I talk about something about Gaussian process. And first step, we are going to review some materials we talked about before. And let's recap a little bit. So in basic methods, in unsupervised learning settings, remember the Bernoulli distribution and categorical distribution for inference density of thousand points or something. First, we have likelihood, which is what? Which is parameter or data given parameters. And then second, because if we just estimate this, maximize this likelihood, we are going to have some overfitting. So we want to integrate some prior into the estimation. So we put a probability distribution over theta. So the third step, this represents our belief about the theta. So if there are some increases in theta, which has very small probability, we are unlikely to pick up that theta. And with this, with likelihood and prior, we can compute the posterior of the parameter given the data, which is using base rule. This is equal to likelihood times prior over the model evidence PD, which is almost a constant in a certain problem. So the first step, we are going to predict, given a new data X, we are going to predict this probability given the data observed and the prior. So the predictive probability Px, like this is a new x, given the data we observed, is equal to this Px given theta, P theta given D theta. So what does this mean? So what's the meaning of this integral? This is a posterior distribution of theta, which means given the belief, given the data we observe, what's the distribution of theta? And this probability is with a certain theta. What's the probability? What's the distribution of the new x? This is almost like averaging, because. For example, if we have a theta which has a very small probability, and then when we times this and this, we have a relatively small value, because this term is small. And if we have a theta which has a higher probability given the data, which means it's very likely to have that theta, and then given that theta, and then we compute this term. And this term, we're going to have a higher weight. So which means, well, if it's more likely, this value matters more. It's like averaging. In a lot of machine learning algorithms, for example, supervised machine or linear regression, we only pick up a certain parameter which is very likely to be the case given the data, and plug in the estimated theta here, and suppose that's the right value of theta, which is inappropriate, because even given the prior and the data, there are still some other thetas which is likely but not very likely compared to the estimation. So we cannot throw away this theta. We still need to consider it, but giving it a relatively small weight. So this kind of prevent overfitting because no matter your, well, we are going to use all possible theta, but assign different theta different way. So it kind of prevent overfitting. This is unsupervised setting. Because there is only x, there is no y, so it's like density estimation or like clustering. And another form is like supervised form. So in supervised learning, we are going to predict y given an input x. Input x is kind of called feature or whatever. And of course, the data. In a traditional way, we usually separate this into two steps. The first step is using data to like train a model first, train a parameter, and the second step you plug in x and with your trained model and get a y. But in the Bayesian mode, the Bayesian settings. This is more like inference rather than like traditional sense. This is y given x, e is the same, and theta, which is a lower parameter, times p theta given x, e. It's almost the same thing which is here, but the only difference is now it's supervised context, so you have like input x, you need to plug into this probability. This part is really nice because it's a model we are assuming. It can be a linear model or it can be any other form. We propose this distribution, so we know how to compute it. But this part, the posterior distribution of theta given x and e, usually is not so nice. Sometimes it can be a bimodal. It's not. Sometimes it cannot. Sometimes you can even easily draw samples from this distribution. This part is nasty. This part is nice. And usually this integral is difficult to compute as well. This is nasty. Usually this form is intractable. To deal with this, this is more like a big picture of like Bayesian methods. To deal with this problem, these two nasty components, there are quite a few algorithms developed. One we can do exact inference. And if you choose Gaussian distribution for these terms, and for multivariate Gaussian, no matter you multiply, you divide, you marginalize, or you condition on a Gaussian, it's usually give you back a Gaussian process, Gaussian distribution. If you choose Gaussian of these two terms, usually you can get back a nice analytical form, so you can solve it really. So the first choice is you use multivariate Gaussian. The Bayesian linear regression is one example of this. You use Gaussian for both terms, so after multiplication you still get back a Gaussian, and you can do a computation easier. And another choice is you choose conjugate prior for this term, the posterior distribution of the theta. I think Sean talked about this before, and we did again a few weeks back, which a conjugate prior, which means if you choose a prior for the electrical term, the product of these two terms give you back the same distribution in the form of the prior. So you choose this to simplify this term. But the benefits of choosing this is give you a nice analytical form of priors. But this is not always what you want. For example, if you want a multimodal distribution or some weird distribution which is not completely prior, so you have to change your problem to use this complete prior. And another way is using point estimate. The two examples is the MLE, maximum likelihood estimation, and the maximum posterior. In these two methods, MLE like theta, MLE is equal to R max P D given theta. And MLE is the switch is two term. So which means instead of doing an integral, you choose one particular value, MLE or MLP, and put it here. And because you choose one particular value, this probability is going to be 1. So because you choose this one value, it's forever equal to that value. So this integral becomes only this term with theta, MLE, or MAP. But if you choose this way, then even though you choose the prior of theta, you are still very likely to have overfitted the data, because this is still point estimate. You just choose a single value of theta. You don't consider the rest probable value of theta, which means you are probably going to lose some important information. And so this is point estimate. Another way to do it is you can do like stochastic approximation, which means you use sampling method. Usually the sampling method you can use Monte Carlo. Markov chain Monte Carlo. You can use like GB sampling or Metropolis. This basically you get points. You sample from this distribution, and because if the distribution, if you have high probability of theta, you are going to sample more theta of that value. So you sample all this theta and calculate this term and do a mean of all the samples. You are going to get the expectation of this form. Or you can do, for example, important sample, which is still actually MCMC. This is the third way. And there's still one way to do it, one more way to do it. You can do a deterministic approximation.